Okay, so to recap a bit of what we did in the document camera, just I think it's helpful to have it on the slides as well. We talked about how to calculate a confidence interval formula if you know the population standard deviation. If you know the population standard deviation, great, use that formula, it's going to give you the best estimate. If you don't, which is more likely, we use the sample standard deviation to approximate the population standard deviation, and we estimate it. We plug in S instead of sigma into the equation, and we can substitute it in the confidence interval formula as long as we have a large sample. Then we have the same steps to calculate it. Literally the only thing is different is that we've substituted the sample standard deviation for the population standard deviation. But here it is on the slide, a bit more formally than me scribbling it on the paper. All right, so as promised, our last order of business is what to do if the sample is small. So you want to calculate a confidence interval, you don't know the population standard deviation, and your sample is smaller than 30. If those things are the case, you can't use the formula that I showed you before, where you're just swapping out the sample standard deviation for the population standard deviation. Instead, you have to turn to a slightly different kind of sampling distribution, which is referred to as a t-distribution. And t-distributions are really, really similar to normal distributions. The main difference is that as you get into small sample sizes, they have different shapes. And this has to do with the fact that when you're estimating a standard error of a sampling distribution, so when you're plugging in your sample standard deviation instead of your population standard deviation, you have a bit more uncertainty about what the real values are when you have smaller samples. And so, in other words, t-distributions are sampling distributions that reflect this estimated standard error. They show you the probability of getting different sample means when you're estimating the standard error. And they have different shapes for different sample sizes. Another way of saying this is that they have different shapes for different degrees of freedom. And when you're using one sample to calculate a confidence interval, the degrees of freedom are very, very closely just based on n. So you can calculate degrees of freedom by just subtracting 1 from whatever your sample size is, which you're not going to have to actually calculate any degrees of freedom here. That's just where they come from. But what you can see on this chart here, which shows different shapes for different degrees of freedom, is that when you have more degrees of freedom, you have a distribution that's taller and has kind of narrower tails. And when you have fewer degrees of freedom, you have a distribution that's flatter and has wider tails. And the technical term for these is fat tails. So t-distributions have a lower hump and fatter tails for smaller sample sizes. They also happen to be normally distributed when your sample size is greater than 30. So this is why, in the last example, if we had a sample that's greater than 30, we didn't have to bother with the t-distribution, because it has the exact same shape as a normal distribution when your sample size is greater than 30. So even if you're estimating the standard error of your sampling distribution, because you don't know the population standard deviation, you can use a normal distribution to do whatever you're going to do, because even though you're estimating it, your sample's big enough that you don't have to account for this extra uncertainty that you have, and you can just use the normal distribution. So before, we were swapping out our estimated standard error for our known standard error, and we were still using the normal distribution because even though estimated standard error puts you into t-distribution territory, large sample sizes kind of take care of all this extra uncertainty that the t-distributions are supposed to be accounting for. Otherwise, t-distributions can be used exactly like normal distributions, with the main difference being that instead of calculating z-scores, we calculate t-scores. They can also be called t-statistics. And you'll probably hear me switch back and forth in this class. So a t-score, like a z-score, is just a standardized score that tells you where a particular value falls on your standardized t-distribution. And t-distributions are generally used when you have an estimated standard error. So you're making a guess about what your sampling distribution looks like based on your sample standard deviation. And especially when you have small samples. T-distributions also have a lot of other applications in statistics, and there are some things we're going to do in the next couple of weeks in this class that they just bypass the normal distribution completely, and we just go to a t-distribution because t-distributions account for everything, and you don't have to worry about your sample size once you're using a t-distribution. But that's next week's problem. So for this week, I just want you guys to be familiar with the t-distribution, the fact that it has different sizes different shapes for different sample sizes, and that it accounts for the extra bit of uncertainty that you get in your estimates when you have a small sample size. So the last thing I'm going to do is hop back over to that document camera, doing, as I do, and kind of give you a brief recap of the t-distribution, talk about the confidence interval formula that uses the t-distribution, and then just recap what you would use when. And then I'll call it a day.